Okay, so thank you so much, and sorry for some shaky start with this new technique for me. So I usually go to other platforms for presentation. So Luciana, thank you so much for the very kind introduction, and to you and Giuseppe and Liberato, thank you so much for inviting me to this talk. So really glad to be with you. And I'm going to talk today about extrusion-based digital construction, opportunities and challenges. And let me start with a reference to other fields. So if you look at these images, you see products which are not common in construction industry, but this is products which are in the media. And if you look at these runners, you can actually just make a 3D scan of your unique feeds, and then you get 3D printed runners which really fits very much your feet. It's maybe even more important if you have some problems with your hips and you need an artificial joint, then it should match. And again, 3D printing is very good. So in medicine, we use this technique very successfully. And finally, the example here on the right is from mechanical engineering. In this field, we have many startups which are very successful, and it seems to be a good business. But the question is if we can use such techniques also in construction, if we can print a house. And you see on this image, yes, it works. But if you look a little bit more attentively, you see that the house is pretty small. So it's printed in a box, and it's printed in this case with polymer material, which is easier. So to print with polymer is relatively easy. You can do it even at home. But how to go one step further, bring 3D printing on the construction side to print on a large scale. And in this case, of course, we need other types of materials like concrete, which are hardened not physically, like polymer, which we just can bring at high temperatures, melt it, then we deposit materials, and very fast it can harden by cooling. In case of concrete, we have a chemical drilling process, and it's much more complicated to steer this process specifically under the condition of the construction. But of course, we expect some benefits. So we don't need, for example, the formwork, which there's a lot of time and energy and money, of course, but it's not the only reason. There are a few driving forces which I want to introduce very briefly. On the first glance, we have, of course, here a lot of the geometrical freedom, and of course, the architects want to use these possibilities. On the other hand, we also can bring here topological optimization of the construction forward. So we can spare material, we can produce more elegant structures. We can also use this internal space for some installations, etc. And of course, we also can consider how this kind of structures can also fulfill functionalities like, for example, installation function, etc. Well, on the other hand, we have really quite great concern with productivity. So in the construction industry, productivity is very low, so it doesn't increase over decades already. In comparison to other branches of economy, it's really not a very good condition. And at the same time, we have more and more trouble to find skilled labor to conduct the construction processes. We also have to pay more nowadays for the skilled labor. On the other hand, the price for robots decreases, and it gives us opportunity maybe to reconsider the cost structure and use more robots in the construction industry. And finally, it's a good news. We have already quite good progress with respect to the digital planning. It means we have all this data, and we should use this data directly for the automated construction. So it means we go for digital planning to digital construction directly using the data, not printing this data on just paper and going with this paper plan to the construction site and making all the mistakes we usually do on the construction site. So I will concentrate in my talk on the interaction between the machine and the material as the base for the successful 3D printing. We have here actually very different approaches. I show here just some selection. You see in the middle smart dynamic casting. You see on the right side the selective binding on the example here of D-shape approach. We have also deposition of material by spraying as an example on the right lower corner. What I will discuss today is the approach which very widely spreads all over the world, pretty successful. It's deposition by extrusion. So layer deposition by extrusion, these two examples on the left side. Well, it's one approach, but very different actually implementation of this approach. Here you see an industrial robot with a print head. You see also from the configuration of the print head that obviously the people work here with accelerator added at the nozzle, and the nozzle is pretty fine, so such pretty fine elements with high resolution can be produced. Another example which goes in the same direction but a little bit on the larger scale here, again very flowable material is delivered by pumping to the print head and it accelerated at the print head, and then due to acceleration of the material, the flowability is reduced dramatically, and you can deposit more and more layers. Obviously, the buildability is here fine. So it's example. In this example, actually, the gantry system was used the same as in this example from TU Eindhoven, large gantry robot which can produce elements on the structural side, such as this bridge elements. So this is segments which are printed separately and then put together, and obviously the colleagues use here pre-stressed steel to reinforce the elements. So in this case, you see that other than the two other examples, the nozzle is not circular, but rather rectangular. And in this case, the nozzle rotates with the changing direction of the printing. So let's go further, and I try to summarize here with this image different approaches for deposition of the material. We have here on the left side sort of what we call infinite brick. It means very stiff material pressed through the nozzle, no deformation upon deposition. On the other hand, on the right side of the image, you see here the approach where we have very flowable material, which is highly accelerated. So after some flow, under gravitational flow, we forcefully reach the final shape, and this shape is then kept as it is. And due to progressive stiffening and hydration, we have here a possibility to carry further layers. Well, in most applications, we have here something in between. This is the image shown here in the middle of the slide, where we have some deformation of the deposit material, but it's not kind of a free flow. Of course, depending on the approach, we have a little bit different shape of the filaments, and also the flowability of concrete affects the bond between the layers. So we can also try another classification approach, saying that it's also about the size of the filaments we deposit. In most of the cases, this approach in the middle is used, where we have not very wide, but also not very narrow filaments, which can be used as a load carrying structure, or what is frequently is the case, it's used as a permanent integrated formwork filled later by concrete or reinforced concrete. If we go to the left, we have here approach as introduced at the University of Loughborough, where thin filaments are placed very close together, so forming kind of a monolithic structure. But of course, we have here high resolution, which enables also to introduce this kind of openings. And on the right side, this is approach which we developed at the TU Dresden, where we work with monolithic filaments, really wide and thick filaments, which kind of replace bricks. Of course, we have here decrease in the resolution going from left to the right, but we have increase in productivity. So we should consider both, of course, these parameters. Concerning our approach, which we called Concrete 3D approach, using wide filaments, thick filaments. So what we try to achieve with this approach is following today's architectural and structural design, which means sharp corners, straight geometries, massive cross-sections. We also try to use the common construction machinery as such track-mounted pump, which are already common in the construction industry. It can be further developed for the 3D printing applications. We also try to use concrete according to codes concerning the composition and the properties. So we will have a little time interval before we can really introduce these approaches into practice of construction on a regular basis. And of course, we also want to have a usual or close to usual surface quality of the printed elements, and also very precise printing. Okay, a little video shows how it works. We have first the digital planning. We then transfer this data to the machine. We have here, with this approach, track-mounted concrete pump, and as I told you, the magnetic cross-section with concrete according to the codes. So how far we are in reality now? We have possibility to print concrete layers with a thickness of 15 centimeters and the height of 5 centimeters. As in this example, we use in this particular example concrete with a maximum aggregate size of 8 millimeters. And it's close to the framework which we get from the codes. So this is an example how such printed elements look like. And we are now in the process to further developing the print head. Of course, it's what you see here is just a kind of a prototype, maybe not very fit for the construction side due to the complexity, but we try to shape this print head so that we can really change the width and the height of the layers in the printing process so that we are more flexible in the production. So let me come now to the requirements to printable concrete. I will do it on the example of our technology, Concrete 3D. So first we need to pump the material to the print head. So the material must be pumpable. So the second one is extrudability, which means that the material should be deposited with a particular rate. So we need a particular rate with which concrete comes out of the print head. And we need, on the other hand, also buildability. It means that after depositing the first layer, we should deposit the second layer, or be able to deposit the second and the third and the fourth layer in a short interval after starting our construction work. It means that the lower layers must be able to carry the upper layer. So all these processes, of course, are guided by rheological properties of concrete. On the other hand, these process steps also influence the rheological properties to some extent. And finally, we also should consider the hardened state properties, and they are also defined to some extent by the printing process. First of all, it's about the bond between the individual layers. Okay, let us go through the different steps of the production process. First, pumpability. We have here very pronounced effect of the lubricating layer on the pipe wall on the delivery rate for a given pressure. And we can describe this relationship by using the formula suggested by Kaplan a couple of decades ago already. So this upper formula is valid for relatively stiff concrete, and two material parameters we need to define are the yield stress and plastic viscosity, but not of the concrete, but of the lubricating layer, this thin layer on the wall. So how derive this parameter? We can perform experiments like this using smooth cylinder instead of other geometries which are usual in testing rheological parameters of concrete. In this case, it's really smooth surface is essential. So we call it kind of a tribometer. So if we have a more flowable concrete, then we need another formula where additionally to these two parameters, we also consider yield stress and plastic viscosity of the concrete itself. And in this case, additionally to tribometer tests, we perform also viscometer tests. Okay, using these parameters, we can establish the relationship between the delivery rate and the pressure needed to achieve this rate, depending on the consistency of concrete and formation of the lubrication layer. So you see here on the left an example that we use this kind of measurements and the prediction and compared the prediction with the real measurement on the pipeline. So the pipeline is given here with solid symbols and with the solid line, while the dashed line and here the empty symbols, they give the prediction. And you see that actually the curves are pretty close together. It seems that this approach works really very nicely. We can also use these parameters derived experimentally for numerical simulation of the movement of concrete in the pipeline. In this case, we use the material law separately for lubricating layer and for the rest of the concrete in the pipeline. And by performing numerical simulation, we also can very nicely observe different phenomena like formation of the plug and region of the sheared concrete. And what we also can observe in this example in particular, how much the changes in the pipe diameter here from 125 millimeters to 100 millimeters change this shape of the velocity profile in concrete. And you see that the plug region, and this is in this case, is much smaller than in the case of a little bit larger pipe diameter. So finally here, I want also to address the possibility to get pretty directly input for prediction formula by using not the sophisticated tribometer or viscometer, but rather this kind of a slide and pipe rheometer, which mimic the movement of concrete directly in the pipeline by actually moving here concrete in a small pipe and measuring here the pressure established on a sensor. So actually we can extrapolate, and this results to a real pipeline, and our experience is very positive with this approach. We have really very, very good prediction of the real conditions in the pipeline. Okay, it was pumping. And now let us proceed to the extrudability. And in this case, it's really about delivering exact amount of concrete per time interval or per time unit. So if you deliver 2 liter material, you will have some interruptions in the filament. If you deliver too much material, you will have some kind of wave here. And of course, if it's go on from one layer to another, you will have accumulation of this imprecise material deposition and finally a severe damage of the structure. So what we need here is, of course, a very good control of the material flow, and we can achieve this by synchronizing the motors, all involved motors moving the print head, but also motors of the pump delivering the material, But what is the trick, I think, is that these synchronization parameters may vary considerably depending on the properties of the fresh concrete, which may also change during the printing process due to aging of concrete in the first hours. We can have some changes in these properties, and then we need to adapt, of course, the steering of the machine accordingly. Okay, of course, also here some formulas can be very helpful. You see here the formulas for predicting the forces needed for actually extruding material by using a ram extruder. And here it looks really good. We have quite clear formulas, which I will not explain in detail, but you can find it in the literature, which is given here. So you can really link the extrusion rate to the extrusion forces directly. However, we do not really use a ram extruder in the practice very much because it's not really suitable for large geometry, for large printing. What is very effectively used is a screw extruder, which looks like shown here in this sketch. We have here quite stable flow, but it's not easy to describe the exact quantity per unit delivered because we have also here some backflow. And again, depending on the consistency of concrete, on the rheological properties of concrete, that backflow can be more or less pronounced. So for usual screws, it's a really difficult task to predict even the quantity we deliver for particular, let us say, number of rotation per time unit. What is easier to do it for progressive cavity pump, which is kind of a screw, but it's a very specific one. Here we can predict the quantity delivered per, let us say, a rotation of this screw. We can predict it pretty accurately, but what we still cannot predict is the needed energy or needed force to deliver this quantity depending on the properties of fresh concrete. So it can be done in the near future, we hope, by using numerical approaches and then understanding better how it works, and maybe on this basis also developing some analytical formulas. So this is the work in progress at in our group. What we also can do is predicting quite accurately the flow of the material in the print head and synchronizing it numerically with the movement of the print head. So finally, I want to address an issue which, at least in our group, we observed in the experiments, so that at least for particular composition of printable concrete, the prediction or rather the behavior with respect to the energy consumption in the experiments with the cavity pump is different if we compare to the ram extrusion experiment. So again, I don't want to go into detail, but what I'm trying to say, if you test your material with ram extruder, it doesn't mean you can translate this result directly to the progressive cavity pump. So it brings me to, again, little conclusion. With respect to the testing, we still have to develop meaningful approaches to predict the extrudability. And at the moment, the most, let us say, accurate procedure is to use the same type of extruder as you use for the actual printing for characterizing the material. Then you have really very accurate prediction of your printing process eventually. So I come to the buildability now, and we proceed here in the first place by printing just the wall elements, simple wall elements, and looking when they fail. So actually the failure is here the goal of the testing, and of course it's not just the failure, but also looking at yours. And in this experiment, obviously this goal was achieved, even if my colleague here is a little bit astonished, but then if I would continue the video, you will see that he is actually happy that these results were achieved. It's like also in mechanical testing, so you produce specimen with the only goal to destroy them, so to get the results. So in this case, the result is the height of the printed element, which hopefully corresponds with the prediction. So how to come to such prediction of the height? So we consider here the balance between the gravitational force, which is described here. So it's the dead weight actually of the element, and of course depends on the gravity constant and the height of the elements, also on the time, because in the process of construction, the structural elements becomes higher and higher. And we have also some effect of the geometry. For example, if you print a just straight wall or maybe some cylindrical structure, etc. So, and in all times, this force need to be smaller, or this actually pressure on the lower layer should be smaller than the yield stress of the material, which develops in time, and this development can be described by using this thixotropy parameter A thixotropy. Okay, both the yield stress and thixotropy parameter can be derived by using rheological tests. However, these tests are not straightforward. I will come right away to this. But what is important, when we have this parameter, we also can kind of shape the process on this base, and you see we, for example, can predict maximum velocity we can afford in the printing process without that the structure collapses. Or if we have some particular understanding about the desired minimum time intervals between the layers, we can actually calculate here which rate of the development of the yield stress, so which A thixotropy should be provided by concrete composition. And we can use, of course, here different approaches to steer the thixotropy of the print material. So, but of course, not just the maximum velocity is interesting, also minimum velocity of the printing might be interesting, and it depends on the printing strategy. It depends, of course, or depends on the economic availability and on the bond properties we want to achieve. Testing static yield stress, and we are talking here really about static yield stress. It means we start such characterization of material really with a shear strain rate equal to 0, starting from 0, and then provided some constant shear rate and looking on development of the shear stress with the increase in shear strain. And then we get some response which looks kind of similar what we also get in mechanical testing of hardened concrete, however, of course, on a very lower level. We're talking here about a couple of dozens of Pascal or even less. So, and then we can perform these experiments at different times after actually mixing concrete, and then you can read here the maximum, and then you can also here deliver the development of the yield stress in time. Usually for the first hour or maybe a little bit longer, you get linear relationship. If you go further due to progressive hydration, you usually get exponential increase. So these two formulas are most often used to describe the material behavior in the first hours. Okay, again, bring us some little summary with respect to material testing. We can say rheological measurements are very good here, so provide a good description of the material behavior. However, they are not easy to perform, so many people go to direct uniaxial compression tests, at different ages to describe the material behavior, which is kind of more straightforward. However, what we see as a very promising approach are penetration tests. We, of course, need here some methodology to translate the measured values into the yield stress, but there are very promising work in progress, and I'm pretty confident that we will have the very good procedure very soon on that. However, we still will need in some cases 3D printing tests just to verify the prediction, so to validate the prediction so that we are sure that our formulas and our test methods are working all right. So, and then also here numerical analysis is essential. You see here that for a printed structure we have in this case actually not the failure of the first layers, but rather structural collapse due to how you call it? I mean, most of you are structural engineers. You understand what I'm talking about. Buckling. Now I have the right word. And you see that it happens not in the corner, but rather on the straight segment of the wall, which also could be expected from the structural perspective. So this kind of finite element analysis of the construction process, not of the final product, let us say a bridge or some house, but of the process. So how it develops in time, it's very essential for the success of the 3D printing. So now, finally, I want to summarize all what I said about actually material testing. So you see that we have actually here a number of different approaches, and we need to develop these approaches further and to make them really feasible for practical applications. But what we cannot rely now on a very simple test, like, for example, split table test or slam test, and say one test would be enough to deliver the entire information needed for the description of the rheological properties. So we need here a more advanced approach on material testing. So let me say also a few words on properties of print concrete in the hardened state. We have here, first of all, the effect of the time intervals on compositional concrete and the roughness of the surface on the interlayer bond. And the interlayer bond affects to a great extent the degree of heterogeneity and also a possible anisotropy of the material. So we studied this phenomena by cutting out of the wall such prisms in different directions and testing them in different directions. Of course, you can expect some effect of these layers depending on the orientation of the layer related to the force we apply. And you see the parameters under investigation, the time interval, composition, and the age of the concrete element. So what we observe that composition exhibit here a really very pronounced effect on the material performance depending on the orientation of the layers. So for the composition based on the Portland cement without addition of supplementary cementitious materials, we have a very pronounced decrease in flexural strength for especially time interval 1 day, but even after 10 minutes, the decrease is quite pronounced for, let us say, unfavorable orientation of the interface parallel to the force. But we do not observe this strong decrease in the case when we use some other mix. I again cannot go here into detail, but you have here the reference you can have a look on. In the case if we use here a mix with addition of supplementary materials. So, of course, we get even more information if we look on this interface area under microscope. You see that different voids can form here, and we have also information of some products like calcium carbonate, etc. Again, I have no time today to go here in more detail, but obviously there are different ways to control the quality, and we will see later on this quality of the bond affects not just mechanical properties but also durability performance. So what we see in few cases in 3D printing that we have some cracking, and we have also some untight joints which after some rain can be seen in this example quite nicely. And it means that we should take care of the bonds also from the perspective of the durability, but also we should take care on cracking, which might be used by shrinkage. And we have some work in progress on that. In this case, we, I believe that now you can see that we produce here an element where the layers had different time intervals. So here in this case is just 2 minutes between the layers, but the last layer was deposited after 24 hours. And you see that only in this position of the interface we have really quite pronounced capillary suction. So these measurements were used or were performed by using the neutron radiography, which enables us to monitor the movement of water in the printed elements. Okay, so you see here that obviously the time interval between the layers is really essential also for durability. Of course, 24 hours between the layers is kind of a extreme case. Usually we want to print without interruptions, but in some cases, of course, it can be accurate, and in this case, we need maybe some additional measures to establish a good bond between the layers. So testing plastic shrinkage, which is obviously quite interesting case here because we do not have formwork, so the plastic shrinkage occurs here right from the beginning. We have no protection also for the walls, and in normal case we do not care about the plastic shrinkage in the walls because we have formwork for the first couple of hours, but in this case not. And what I want also to address that for stiff types of concrete we use for 3D printing, of course, this kind of setups are not acceptable because we cannot really place material without much trouble and such molds. So we need to go to other solution. In a running project, we have some research on this, on plastic shrinkage of 3D printed concrete, using here some specific setups on observing the crack development. So we use also some numerical analysis approaches to look on the development of the capillary pressure and shrinkage deformation before we come to conclusions concerning the possible cracking. So another challenge is fabrication of inclined elements. And you see on few examples that actually it works quite nicely, of course, up to a certain degree. So we cannot go here to absolutely horizontal surfaces because we have no enough support for this. In this case, often you see examples like this, just a piece of wood placed as a support. I think in such application, more elegant would be to use maybe textile reinforced concrete as a kind of support, as a kind of a lintel in this case. What we also suggested is to use other 3D printed material, which is kind of disposable. In this case, we use a mix of wood chops and starch to produce a material which is serves here as a support material, but that can be removed easily and recycled and used again for further applications. Otherwise, if you have more, let us say, fancy geometry, you can also use this kind of curved mold and deposit material on this mold, again using 3D printing, as this example from Loughborough shows. Well, just to show you also the width of possible materials we apply in 3D printing, in this case, we successfully used foam concrete for 3D printing. Of course, it's quite challenging, but it works. Now I see that I still have about maybe 9 minutes. I want briefly to address the matter of reinforcement. So one possibility is what we see here, to print the formwork and then to use this formwork as an integrated formwork by placing more or less in a conventional manner the reinforced concrete inside it. So in this case, just vibrated concrete. So it would be good at least to use the strength and load carrying capacity of this formwork. At the moment, existing codes do not enable this, but at least you can use here the core as a load carrying element according to existing codes. So this is a pretty straightforward approach. Another straightforward approach is to print first the wall and then apply the reinforcement on the printed wall, as shown here in the case of our project. You see there are some mounting elements here, and then you just place the mesh, steel mesh, steel mats here on this mounting, and then apply by spraying or by other technique the cover layer. So, of course, you can use also textile reinforcement for change. Then an example which I showed you already. So you can produce some structural elements with voids, which is often is the case for 3D printing with high resolution. And then you have possibility, of course, to guide the reinforcement through these openings, through these voids, and use it as a common reinforcement or for pre-stressing. External pre-stressing is shown here, again, printed element segments, and then you have here some anchorage, and you connect these elements by external pre-stressing. Very common way is also a very straightforward way is to place conventional or other reinforcement between the layers, but of course it just looks in one direction, so in horizontal direction like shown here. However, we should also consider in this case the corrosion protection. So if we have really enough corrosion protection, because as I showed you before, the interface between the layers can be quite permeable for water and other aggressive agents. Well, interesting approach here from China. You saw just in the video that actually the print head encloses here the reinforcement which are already in place. To do this, you need a large print head here, about 4 meters high, of course, very massive, not easy to move, which really place the material, the concrete, on both sides of the reinforcement, which is already in place. Well, again, a pretty straightforward approach is to put some fiber in print material. Unfortunately, we have nowadays fiber reinforced concrete, which is really of very high performance. As this example shows, we have a strain hardening behavior of the material by additional fiber of about 2%. And we tested this and published about 2 years ago. So you see here that SHCC as a strain hardening cement-based material can be printed. We produced, again, walls of different sizes. We cut the materials, specimens out of these walls. And we observed that indeed, by having 1 or 1.5% of polyethylene fiber, we achieve a very good performance at least in the direction of printing. Unfortunately, perpendicular to this direction, when we cut the joints, the performance is not that good, but we are looking for options to improve. So finally, I want to introduce a novel type of reinforcement, which I see as a very good candidate for application in automated construction. It's about carbon yarns, which are impregnated with mineral-based suspension. You see here some steps of the process, and we get then bars, something like this. But what is good, we can make this process as an inline process, or we can produce this kind of a spool with the reinforcement and then apply it on the, let us say, head of the robot to produce different shapes, such as shown here. This is a reinforcement for a shelf structure, and in this image you see some other elements for a balcony, or here for a beam, or even umbrella can be produced if you need a concrete umbrella reinforced, so you can produce it easily. So what we are doing now, we are trying to integrate this type of reinforcement directly in the 3D printing process, as shown here. We have the different approaches. You can find some information on this in the recent publication of us in Materials. So it's an open access journal which you can easily find on the internet, and you can download the paper. So you see that we also use here, or trying to use deposition in the vertical direction, and I hope that we can also show some results soon enough. So thank you very much for listening. Of course, also many thanks to my group. These are people who actually produced the results which I just presented to you. And just for the case, if you understand German and are interested in this topic, you are welcome to join our online conference end of October. Oh, the conference I say here in Dresden, but actually it will be online, prepared by our group. And with this, I again thank you for your attention, and I will be more than happy to answer your questions.